Hi there everyone and welcome back to the channel. If you're interested in Cinewhoops, then this AOS projects update video is for you because we're going to be looking at a whole family of new AOS Cine frames. The Cine20, 25, 30, 35 and 40. That's right, we've got a whole family of frames from 2-inch all the way up to 4-inch props to look at. And in this video, I'm going to be taking you through the key features of this new family of frames on the bench. We're going to be looking at some example builds and talking about recommended parts. I'm going to be taking you through some Blackbox log analysis, and we're also going to be looking at a bit of flight footage. By the end of this video, you're going to know everything you need to know about these new Cine frames, how to build them out, what they're each capable of, and which one is going to be right for your next shoot. It's a lot to cover in one video, so let's not waste any more time, let's dive right into it. As always, check out the links down in the video description for all the specs, build guides, and recommended parts lists for all of these frames, and make sure to search AOS Cine in the Betaflight presets tab to find the custom PID tune for each and every frame. Alright, let's start by looking at the baby of the family, the AOS Cine20, and starting at the front of the frame with this brand new anodized aluminium camera cage, which doesn't just look awesome, but it also provides the best possible protection for whatever camera system you choose to mount in this frame. I've got the DJI O3 camera mounted at the moment, and you can see it's soft mounted and there's full support for ND filters. But you can also use any of the Walksnail cameras, any 19mm analog camera, or even a 14mm nano camera. Moving backwards, we've got hard points for a lightweight action camera. They are 27 by 18mm M2 pattern, and the rear mounts are reinforced with press nuts, so you can just screw straight down into the top plate. Then we have this battery plate here with a captive battery strap so that you can secure your battery, and there's support for both lengthwise and toilet tank mounting depending on how you want to mount the battery to the top of the frame. To the rear of the frame, we also have another 18 by 27mm M2 mounting for an action camera if you want to do a reverse shot. And then there's a cutout for a panel mount XT30, or also works with a standard XT30 as well. We have a 3D print, and the STL file is available on aosrc.com for this, which can hold the Express LRS 2.4 GHz T-style antenna and the O3 antenna, or a standard 4mm antenna. In terms of motors, I'm using 1303 motors on this drone, but you could also use 1204s. Both of those would be the right size, with 2-inch props. And the frame is designed to be used with a 25mm AIO flight controller and a digital VTX, something like the DJI 3 or the Walksnail Moonlight 4K or HD Freestyle V2. Any of these sort of larger digital VTXs will fit, and of course a smaller analog style VTX will also fit. On the bottom plate you've got 25 by 25 and 20 by 20 M2 mountings for whatever VTX you choose, and the mountings for the 25mm AIO are also reinforced with press nuts, so you can get a super secure and stable mount for the flight controller. There's also 20 by 20 mountings for the flight control stack, but I recommend you use a 25mm AIO with this build. The battery plate is designed to support a captive battery strap, and there are slots either for lengthwise battery mounting or toilet tank, depending on what you prefer. All of the prop guards are 1.5mm carbon fiber, and the screw holes have been reinforced for extra durability. There are STL files for 3D printed TPU bumpers if you need extra protection for the prop guards. And if you want to save weight, you can also fly without the prop guards, so you can just remove the 2 prop guard pieces and fly without them. Similarly, if you are keen to save even more weight, you can swap the camera cage for just a couple of M2 standoffs, 25mm, and then use a 3D printed camera holder. That will be lighter, but won't provide the same level of protection for the camera that the aluminium cage offers, but it is an option. Now seems as good a time as any to talk about frame weights. And I know that a lot of you guys are running to weight restrictions, either 250 grams or something else, depending on what work you're doing. So frame weight is important. If you're running with the metal camera cage and the prop guards installed, then you're going to get the weight in this column here, anywhere from 42 grams for the Cine20 up to 207 grams for the Cine40. That is going to save you a bit of weight compared to a typical Cinewhoop, so anywhere from 10% up to maybe 25% compared to a typical Cinewhoop. And that's going to give you some extra weight to either run a bigger battery or use some 3D printed prop guard bumpers to provide additional protection when you're flying around. Where things get interesting is if you decide to run without the metal camera cage and without the prop guards. Now you can save a lot more weight. You can save about 6 grams moving from the metal camera cage to standoffs and a very lightweight 3D printed mount. And you can save even more weight if you choose to run without the prop guards, anywhere from 15 grams up to 47 grams. Now I know that if you're flying around inside or close to people, you're not going to be able to run without prop guards. What I'm thinking is that if you are doing some shots inside with prop guards and then you go outside, you can take the prop guards off, save the weight, run a much bigger battery and get longer flight times or more performance for those particular shots where you don't need the prop guards. Obviously, you're probably going to be running with prop guards most of the time if you're flying proximity or close to people. Before we dive into looking at the Cine25, I'm sure you will have noticed while we were looking at the Cine20 on the bench that it leans much more towards an open prop design than it does towards a duct. And there are a few reasons for this that I wanted to go into. The first is weight. Ducts are heavy, and with a lot of pilots running to weight restrictions, if you can save weight on the duct by moving to an open prop, more of an open prop configuration, you can run a bigger battery for longer flight time, and that's beneficial. The second is flight performance. It's well understood now that ducts for FPV quads don't really offer any additional thrust or efficiency over an open prop design. So having an open prop design is going to give you better flight performance, particularly at high speeds, because you don't have the duct drag phenomenon. So that allows you to achieve higher speeds, and it also makes the quad a lot less susceptible to wind and turbulence in the air, which can really badly affect ducted quads because they've got a big surface area for wind to push against and for turbulence to perturb the movement of the quad. So an open prop configuration is going to give you smoother flights, particularly in windy conditions. It's going to let you cruise at higher speeds more efficiently, and it's going to save you a lot of weight. So that's why all of these designs lean towards an open prop. That said, of course, it's configurable, and you can find down in the links in the video description STL files to completely shroud the props, create a duct if you want the duct drag phenomenon. So you're wanting to fly slowly in close proximity to targets, and you want the duct drag because it gives you more precision at low speed in still air, then 3D prints are available for ducts for all of these frames. Now let's look at the Cine25, and this shares all of the same key features as the Cine20. Obviously it's just been expanded a little bit for 2.5 inch props. We've got the same camera cage at the front available in your choice of colours, and this is a lovely green one. And we have mounting patterns for lightweight action cameras at the front and rear of the frame. Again, captive battery strap slots with support for lengthwise and toilet tank battery mounting, and a fully integrated XT30 VTX antenna and receiver antenna with the 3D print at the rear of the frame. If we turn the frame over, we've got 2mm prop guards now, and again they're reinforced for extra durability. You can choose to fly with or without the prop guards, and there are STL files for TPU bumpers available. In terms of motors, we're now using 1404 motors to drive these larger 2.5 inch tri-blade bullnose props. That's what I'd recommend. Again, we're looking at a 25mm all-in-one flight controller and a VTX mounted to the base plate. And you've got 25x25 and 20x20 M2 mounting for the flight controller and the VTX, with the 25x25 for the flight controller reinforced with press nuts. As before, you can choose to build with or without the prop guards and with or without the camera cage, depending on what you're looking for. Moving up another step in size, we have the AOS Cine30. Again, all the same key features as the Cine20 and 25 that we just looked at. We've got the same anodized aluminium camera cage, your choice of color. This one's in a lovely red. We've got mountings for the action camera, front and rear, captive battery strap slots for lengthwise and toilet tank mounting, fully integrated XT60 now in the rear of the frame, so you can choose XT30 or XT60 for the Cine30, and obviously VTX and ERLS antenna also integrated. This has again a 2mm prop guard with reinforcement for all of the screw holes, with STL files for bumpers available. The link's down in the video description. I've decided to build this one out with the Cadex Moonlight 4K system. So you can see the camera mounting fits just perfectly in the camera cage. And again, we're looking at a 25mm AIO with space for even a large VTX like this Cadex Moonlight VTX. In terms of motors, again, we're moving up a little bit in size. So I would say anything from a 1505 to a 1606 or maybe even a 1507 motor for these 3-inch tri-blade bullnose props. That's going to give you plenty of power. And that's the Cine30. As we move up to the Cine25, again, the platform expands a little bit for the larger props. And the action camera mounting in the front and rear of the frame moves from 27 by 18 M2 up to 28 by 28 M3 to support larger full-size GoPros. Again, we've got the same camera cage in the front, your choice of colours. This one's a lovely blue. And the battery mounting plate has now moved up to M3 screws to support the heavier battery that you're going to want to be running on something like the Cine35. Again, lengthwise and toilet tank mounting is supported with slots in the battery plate. The rear of the frame has an integrated XT30 with a VTX antenna. All the print files are available in the video description. Again, we have 2mm thick prop guards with reinforcement around the screw holes, and 3D printed TPU bumper STL files are available at the links in the video description. We're now spinning a slightly larger 3.5-inch bullnose prop, so I would recommend anything from a 2004 up to maybe a 2006 motor for this, and recommended parts and specs are all at the links in the video description. Again, you can choose to run with or without prop guards, with or without camera cage, depending on what you want to do. And again, we're looking at a 25mm AIO flight controller with plenty of space for a large digital VTX, and 25 by 25 and 20 by 20 M2 mounting for the VTX and the flight controller. Again, 25mm mounting for the flight controller is reinforced with press nuts. Last but by no means least, let's take a look at the AOS Cine40. And there are a couple of differences with this frame compared to the frames we looked at previously, so let me take you through it. Up front, we have the same anodized aluminium camera cage in your choice of colors, and this one's in black. Behind it, we've got a 28 by 28mm M3 mounting for a GoPro. The battery plate, again, space for captive straps, and you can have lengthwise or toilet tank mounting. And behind it, we have another 28 by 28mm M3 mounting for an action camera for a reverse shot. And there's also a fully integrated XT60 and Express LRS 2.4 GHz antenna with a 3D print as on the other frames. Unlike the other frames, there are two SMA antenna hardpoints on the top plate, and they're designed to allow you to mount larger antennas like this for really good video reception at longer ranges. They are rigidly mounted, and they're mounted in the middle of the frame to minimize vibration. If we turn the frame over, we've got a slightly different configuration of the bottom of the frame. The prop guards are 2.5mm, and the M3 screw holes are reinforced, and there will be 3D printable bumpers available for these prop guards as well. Links down in the video description. We now have a center section of the base of the body that's raised up compared to the plane of the prop guards, and that's to allow you to use a larger stack in this build. So I've got a 2-board 30 by 30 stack and then a DJI O3A unit above it, and there's plenty of space for all of that. You can also of course use any other digital or analog VTX, and you've got 25 by 25 and 20 by 20 mounting for the VTX on this bottom plate, and 30 by 30 and 20 by 20 M3 mounting on the main plate for the flight control stack, with the 30 by 30 mounts reinforced with press nuts. In terms of motors and props, I'd recommend a 4-inch prop, either an open prop like this or a tri-blade bullnose if you're lifting a heavier camera, and a motor anywhere from 2306 to maybe 2207 in size, again depending on just how much weight you're lifting, with about 2000 kV on 6S. And that's the AOS Cine40. So now that we've taken a look at all of the key features of these frames on the bench, it's time to do a black box log analysis. And vibration and resonance performance is so important for cine frames like this, because what we're looking for is vibration and jello-free footage at all throttle positions. So we have to avoid any frame resonances, any mid-throttle oscillations, anything like that, no matter what throttle you need to fly at. So let's start by looking at the Cine20, and this is the smallest frame with the smallest props, and therefore we have the highest prop RPMs. So we're getting RPMs anywhere from 400 Hz up to 800 Hz at full throttle, and we just see one band of motor noise because the second and third harmonics of the motor RPMs are at such high frequencies that they're going to be filtered out by the internal filters inside the gyro chip itself, and we never see them in beta flight. We only have that one band of motor noise, and you can see that there's no visible frame resonances on roll, pitch, or yaw. And what this means is that no matter where you have the throttle set, there's no resonance for you to find with the throttle position. So you're not going to get any mid-throttle oscillations. You're not going to get any jello or vibration in your footage, no matter what throttle setting you're at. Looking at a slightly larger frame, this is the Cine25. So because we've got larger props, they're spinning at a lower RPM, and we have motor noise anywhere from about 160 up to 481 Hertz. And again, you can see that we just have one band of motor noise and no visible frame resonances across the whole throttle range. Just as with the Cine20, this helps eliminate mid-throttle oscillations because no matter where you set the throttle, there's no resonance for you to find in the throttle band. With the larger frames like the Cine35 or the Cine40, we do start to see the third harmonic of the motor RPM appearing in the Blackbox logs. And this is because with these larger props, they're spinning much slower, particularly at low throttle, and therefore 3 times the motor RPM, or the blade passing frequency for tri-blade props, starts to be able to get through the internal filters in the gyro chip, and we see it in the logs in Betaflight. Obviously, Betaflight is going to be taking care of that with the third harmonic of the RPM filters, so you're not going to see it in the post-filter data. We do see it in the pre-filtered gyro data. Apart from that, we don't see any other frame resonances or anything that would provoke mid-throttle oscillations, and so no matter where you are in the throttle, you're going to get nice, smooth, jello-free footage. Now that you've seen the resonance performance in the Blackbox logs, I also wanted to give you an explainer of how this resonant performance is actually achieved in the design of each of these frames. And to do that, we're going to be looking at the Cine40 and some resonance simulations that I've run so that we can look at how the mode shapes interact with the resonant frequencies. All of the new AOS Cine frames have very similar frame geometry, so they all have very similar mode shapes, albeit with different resonant frequencies. This is the first mode of the AOS Cine40, and you can see it occurs at 242 Hz, and the mode shape is to have the 2 diagonally opposite motors moving up and down together. Normally, this could cause a problem if your throttle setting is such that your motor RPM is very close to 242 Hz. Then the vibrations from the motors can get amplified through the frame into the flight controller, and that vibration can cause the flight controller to make the quad twitch or jerk slightly, and that can ruin perfectly smooth HD footage. To avoid that, you can see that I've very carefully chosen the placement of the flight control stack mountings to be in between where the arm meets the body of the frame, such that even while the rest of the frame is moving and vibrating because of this resonant mode, none of that vibration transmits into the flight control stack. None of it gets into the gyro, and therefore the gyro is not going to know that the frame is vibrating, and it's not going to react to that vibration and cause the frame to move, twitch, or jerk. And that's why you just won't see this mode in any of the Blackbox logs. That vibrational energy just can't make it into the gyro chip on the flight controller. This is the second resonant mode of the Cine40, and you can see that it's got this sort of bouncing mode shape where the middle of the frame is moving up and down vertically. This is a mode shape that typically is not going to cause us too much problem, provided that the center of mass of the quad is nicely aligned with the flight control stack. We want the flight control stack to be bouncing vertically up and down and not rotating or pitching or rolling, because that will be picked up by the gyro. So this vibrational energy will be seen in the z-axis of the accelerometer, but we have a lot of filtering on the accelerometer in Betaflight, and so we're not going to see anything with such a high frequency coming through on the accelerometer. It's the gyro that we need to be focused on, and provided that we get the center of gravity nicely positioned, we're not going to see any of this resonant mode coming through at all. So now we're looking at the third resonant mode, and this is now up at 404 Hz, so a really high frequency, but we're still trying to avoid anything getting through into the flight controller. Here we've got a kind of slightly different mode where the front and rear of the quad are moving up and down together. The critical element here is to balance the stiffness of the frame in the lengthwise direction such that while the front and rear of the quad move up and down, they do so in a balanced way, such that the flight control stack doesn't end up pitching forward or backwards while this movement is occurring. And that's all about making the frame geometry symmetric across the center line from front to rear. So this is why you'll see that all of the frames have a symmetric appearance from front to back. It's just to make sure that this resonant mode doesn't cause any rotation of the flight controller. And so again, while the frame is moving in this mode, none of the energy from that vibration is making it into the gyro. And so the flight controller isn't going to react to this vibration in a way that would cause any twitches or jerks or anything to disturb the footage. So now we're looking at the fourth mode of vibration of the Cine40. And this is the first mode with any significant transfer of energy into the rotational axes of the flight controller. So you can see that we've got the main body of the frame pitching forward and back. And so that does allow some energy transfer into the pitch axis of the gyro. But this mode occurs at 484 Hertz. That is such a high frequency that you may not even be able to achieve a motor RPM high enough to excite this mode, depending on your choice of motor KV and prop. But if you can, your motors are going to be spinning above 29,000 RPM before they're going to be able to excite this mode. And that frequency is just so high that you've got a lot of gyroscopic stability from the motors at that point, which helps damp down the kind of twisting that you're seeing of the motor mounts. Also, this is a pitching mode, which means if you have a lengthwise battery, which is pretty typical of what you'd want to run on the Cine40, that lengthwise battery is also going to provide some significant damping and help reduce the amount of movement of the main body of the frame. The result of this is that you're not going to see any mid-throttle oscillations below about 484 Hertz with this frame. And once you get up to that very high throttle position, you've got so much damping, throttle pit attenuation, and gyroscopic stabilizing effect from the motors that there's no risk of you getting any twitches or shudders in the footage at all, even at full throttle. I thought you'd like to see, for completeness, one final resonant mode. This is the fifth resonant mode of the Cine40. It occurs at 527 Hertz, and it's the first resonant mode that has any significant energy transfer into the roll axis. Because you're typically running a lengthwise battery, sometimes the energy transfer into the roll axis is actually more important than pitch. And so it's very important that this mode is an even higher frequency than the first pitching mode. I don't know if your motor and prop combination is going to allow you to achieve a motor RPM where you can actually excite this mode. And if you are able to, if you've got sufficiently powerful motor and prop combination to do that, it's only going to be at or very nearly at full throttle when you're going to be able to achieve that frequency. At that stage, you've got so much gyroscopic stability from the spinning motors, you've got so much throttle pit attenuation because you're now at maximum throttle, that you're not going to see any sort of twitches or judders coming through into your gyro logs or your HD footage at 527 Hertz. It's just not something you need to worry about. But I just thought you'd be interested to see the final vibrational mode. I hope you enjoyed that technical deep dive into what gives these new AOS Cine frames their excellent vibration and resonance performance. It comes down to careful choice of flight controller stack mounting position and careful balancing of the stiffness of the frame across the pitch and roll axes. It's not magic, it's just a bit of science, but I think that's even more exciting and I wanted to share it with you. If you'd like to try any of these frames for yourself and take advantage of these design benefits, then I'll put links down in the video description to where you can get hold of any of these frames today. And I'll leave you with a little bit of flight footage so you can just see me pootling around with them while I was doing my test flights. I'm not the best pilot, but I thought I'd share a bit of flight footage with you as well. That's all I have for you for today. So until next time, I wish you all very, very happy flying.
Something good. I think we're onto something good. Don't let it get away. This could be everything. You know I gotta say. something good.